Big O is a way to measure the time complexity of an algorithm. It helps us understand how the execution time of an algorithm grows as the size of the input increases in the worst, best, or average case. Today, we're going to quickly go over 8 common types of Big O complexities. The first one is O of 1, also known as constant time complexity. This means that the algorithm's execution time doesn't depend on the size of the input. No matter how large the input is, the time it takes to run remains the same. A typical example would be accessing an element in an array using an index, or checking if a number is even. Next is O of log n, also called logarithmic time complexity. This means that the algorithm's execution time grows logarithmically as the input size increases, but it grows much slower than linear growth. You'll often see this in divide and conquer algorithms. Classic examples include binary search and searching in a binary search tree. The third one is O of n, also known as linear time complexity. This means the algorithm's execution time grows directly with the size of the input. The bigger the input, the longer it takes to execute. Common examples include looping through an array or a linked list, or finding the maximum or minimum value in an array. The fourth one is O of n log n, also known as linear logarithmic time complexity. This often appears in efficient sorting algorithms. It means the algorithm combines both linear and logarithmic growth. Common algorithms with this time complexity are quicksort and mergeasort. The fifth one is O of n squared, also called quadratic time complexity. This means the execution time is proportional to the square of the input size, and it's common in algorithms with nested loops. Examples include bubble sort and insertion sort. The sixth one is O of n cubed, or cubic time complexity. This means the execution time is proportional to the cube of the input size, and it typically appears in algorithms with triple nested loops. A typical example would be matrix multiplication or iterating over a 3D array. The seventh one is O of 2 to the power of n, or exponential time complexity. This means the execution time grows exponentially with the input size. You'll often see this in algorithms that need to explore all possible subsets or combinations. Examples include the recursive solution for the Fibonacci sequence and generating all subsets of a set. Finally, we have O of n factorial, or factorial time complexity. This means the execution time grows in proportion to the factorial of the input size, and it typically appears in permutation problems. An example would be generating all permutations of a set.